In this video, we are going to look at mechanical energy and the application of the principle of conservation of mechanical energy. So we've got a question whose statement reads like this. The simplified diagram shows a slide PQ at a playground. The slide is 3 meters long and 1.5 meters high. A boy of mass M stands at the top of the slide at P. The boy falls vertically down from the top of the slide through the height PR. Ignore the effects of friction. Now the question says use the principle of conservation of mechanical energy to calculate the speed of the boy when he reaches the ground at R. Now most of you, because we are told that section PR is frictionless, you are thinking, well, I could use equations of kinematics. However, it's wrong for this question because the examiner here is asking you to only use the principle of conservation of mechanical energy. We know there's a lot of things that you could apply to solve this question, but however, we want to restrict you into using the principle of conservation of mechanical energy, which states that the total mechanical energy at the initial point is equal to the total mechanical energy at the end point. And also keeping that this must be an isolated system, of which we are told that the boy is going to fall through section PR, which is frictionless. Now, when someone falls, it means that person is not given an initial push. There is no force at the beginning. He falls freely. It means that the initial velocity of the boy is going to be 0 because he falls freely. So VI is equals to 0. Furthermore, since the only force acting on the boy as he falls is going to be the gravitational force, it means our free body diagram for the boy looks like that. The only force acting on something that falls freely is the gravitational force. Very exciting stuff there. So let's try and apply the principle of mechanical energy to find the speed when it reaches point R. The principle of mechanical energy, conservation of mechanical energy mathematically would go the Emech at point P is equal to Emech at point R. Now when we expand this, half mvi squared plus mghi is equals to half mvf squared plus mgh F. Very exciting stuff. Now, what are the things that we know? We know the initial velocity is 0. We are told that the mass of the boy is just m. So the mass of the boy is m. I wonder why is that? All right. Furthermore, when you look at the initial height, the boy starts at P. So how high is P above the ground? P is 1,5 meters above the ground. So our HI is going to be 1,5. At R, that's when the boy is at the ground, and that's our final height. But R is just at the ground, so the final height is just going to be 0 from the ground. So let's apply that. The first thing that is interesting is, since we are told that the mass is m, it means wherever I see m, I'm going to put m, 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 and m, which makes the same m. So even if the mass of the boy I was told to be 20 kilograms or 40 kilograms, I would put the same 20 kilograms there, which makes it exciting because I can just divide by the same m, divide by the same m, divide by the same m throughout. And what am I left with? I'm left with the following. Half vi squared plus ghi is equals to half vf squared plus GHF. Very exciting stuff. However, I know that the initial velocity of the boy is 0, so this whole term is dead. Similarly, the final height, which is at R above the ground, is 0, so the whole term is dead. What am I left with? I'm left with half of VI squared is equals to, sorry, excuse me for that. No, we're doing the wrong things. We are left with GHI and half VF squared. So we are left with GHI is equals to half VF squared. We are looking for VF, this is half, so I can just double everything up. 2GI is equals to, when I double that, it gives me a 1, so I'm left with VF squared. Now, because I'm looking for VF squared, for VF, which is the final velocity or the final speed, I'm going to take the square root on both sides. Vf is just going to be the square root of 2ghi, like that. My g is the gravitational acceleration, 9,8. My hi is the initial height, which is at p. So Vf is equals to the square root of 2 into 9,8 into 1,5. And we're going to put that in our calculator to find the speed of the buoy at p. So the square root of 2 times 9,8 times 1,5. We get 5.42. So Vf is going to be 5.42 meters per second. Very exciting stuff there. So the only thing that you know about the conservation of mechanical energy is that whatever the mechanical energy at P is, that's going to be the same with whatever the mechanical energy at R is, provided that system is isolated. Now, what if the buoy had to go through section PQ? And if section PQ was also frictionless, it would mean the mechanical energy at point P is equal to the mechanical energy at point Q, only if the system was isolated. That would mean also that the velocity of the buoy at point Q would still be 5.42 meters per second.